Welcome to Calculus. We're going to begin our study of calculus with a discussion of what calculus has really done for our world and a little bit about the history of calculus and how it developed out of two very major problems that spurred its development. So what exactly is calculus? Calculus is the mathematics of change. Our universe is constantly changing, and calculus is the dynamic study of all that change. Without calculus, we're very, very limited in our ability to study this changing universe. Pre-calculus mathematics, I don't mean the course pre-calculus. What I mean by that is mathematics prior to calculus was very static. It was unable to really model things that were rapidly changing. The world is changing. There's velocities, accelerations. So let's look at the world without calculus and the world with calculus. Prior to the development of calculus by Newton and Leibniz in the late 1600s, we were unable to do anything with slope other than find the slope of a line. If something wasn't linear in its change, we were unable to deal with it. Well, with calculus, we can actually find the slope at any point on any kind of curve, even if the curve is changing very rapid. Prior to calculus, if something was moving at a constant rate, you could find an average, but the average was not very precise in some cases, especially for things that are very dynamic, changing rapidly. With calculus, we can find the rate of change at an exact moment in time, even if something is changing very, very rapidly. Before calculus, we could find the curvature of a circle and with a lot of help, certain other shapes. With calculus, we can find the curvature of any kind of curve that you can dream up. Before calculus, prior to calculus, we could find the direction of motion along a linear path. With calculus, we can find the direction of motion along much more complex paths, which allows us to have things like satellites. It's not a surprise the world changed drastically after the invention of calculus, and it's not an overstatement to say that it truly transformed mankind because it allowed us to develop complex machines, things that make our modern society possible. And in fact, companies like Google are using calculus today to help modify and create their search engines. Calculus is a very dynamic thing that helps us explore a dynamically changing world. Without it, we would be at a huge loss to be able to model those kinds of things. Looking at area. Prior to calculus, we could find the area of certain shape. With calculus, and you're going to see this is the second major problem in calculus, we can find the area under a curve. Prior to calculus, we could calculate the work done by a constant force. With calculus, that force can vary. Prior to calculus, we could find the center of certain defined shapes. With calculus, the centroid of a region, very important in things like the center of gravity of an aircraft, for example. On and on we can go. Volumes. We could find volumes of predefined objects before calculus. With calculus, much more complex objects. So let's look at the two major problems in calculus. First, the tangent line problem. The tangent line problem was originally, how do we find the slope of anything at a certain point? Now, we could do that for lines. You can do that for lines. You did it in Algebra 1. But calculus allowed us to find the slope of a curve of a function at any point. Well, how do you do that? Well, finding a secant line between 2 points and then drawing the 2 points closer and closer together to where eventually that secant line between the 2 points becomes the tangent line at the point we're interested in. Let's look at an example, and this is the function y equals x squared. And let's pick a point 0.5, 0.25, or 1/2, 1/4. This is the point we want to evaluate the tangent at. We want to find the slope of a tangent line, here it is in red, at this exact point. And that's the crux of what the tangent line problem is. But wait, from Algebra 1, you've got to have 2 points to find a slope. And it doesn't appear that there's any other points on that line that are shared by that curve y equals x squared. Well, you're right, we do have to have 2 points to find a slope. We're going to find a second point, let's call it Q, at some distance away from P, and we're going to find the slope of that blue line, which we're calling a secant line between the points P and Q. Well, you can see that the slope of the blue line and the slope of the red line that we're really interested in, the instantaneous slope at P, and they are not the same slope. Well, how can we get them to be the same slope? we're going to take that arbitrary point Q and bring it closer and closer to P. And you can see as Q gets closer to P, the slope of the secant line becomes closer and closer to the slope of the tangent line. Okay, and what we're going to do an example where we bring it reasonably close. What we're going to do later, after we've understood what limits are, we're going to bring it infinitely close, and then the slopes become the same. So let's look at the example where the function is y equals x squared. And we're trying to find the slope of the tangent line, that's this red line, at point P, which is 1/2, 1/4. So we're going to pick a point Q to start with that's at 1, 1. It's a little distance of the way of P, and you can see that the blue secant line, its slope is different from the slope of the red tangent line. Well, let's find the slope of the secant line, the blue line, using your Algebra 1 good old y2 minus y1 over x2 minus x1. So if we plug in the points for y2 and y1 and x2 and x1, we get 1 minus 0.25 over 1 minus 0.5, 0.75 over 0.5, a slope for the blue secant line of 1.5. As we've said, we want to pick a point that's closer to P. So let's go half the distance to P. We'll go to 0.75, 0.57. Q is a little bit closer to P. So the slope of the secant line, you can see, is already closer to the slope of the red tangent line. If we use y2 minus y1 over x2 minus x1, here's what we get. 0.57 minus 0.25 over 0.75 minus 0.5. You get a slope of 1.28. So we're getting closer and closer, you can see. We've gone from 1.5 to 1.28. But we still have a little bit of the way to go. You can see this blue slope is somewhat greater than the slope of the red line. So let's get even closer. We're going to pick a point Q that's at 0.6, 0.36. It's only 1/10 of a x coordinate away from P. If we do the same kind of thing, we're going to find the slope is 0.11 over 0.1. The slope is 1.1. And that's close enough for now. When we get to understanding what limits are, we're going to bring Q even closer to P, in fact, infinitely so, such that the slope of the secant line is the exact slope of the tangent line. Let's turn our attention to the area problem. As an example, we're going to look at the function f of x equals the square root of x at this black curve here. And we're going to find the area of that purple region that occurs if we just look at the interval from x equals 1 to x equals 5. Now, there's lots of different ways to do that. With calculus, eventually, we're going to be able to find that exactly. We're going to approximate it by using rectangles. And we'll start off by using 4 rectangles. And as you recall, the area of a rectangle is equal to base times height. In this case, we're going to use a term called delta x, which is the change in the x values between the one part of the rectangle to the end of it. In this case, 2 minus 1 is 1, and we're keeping that interval, that delta x, the same. So the base of all 4 of these rectangles we're going to use is equal to 1. The height of the rectangle is f of x. It is the square root of x, in this case, at the leftmost value of x for that rectangle. So for example, on the first rectangle, the area of this first rectangle is equal to the delta x, 1, times f of x at 1, f of 1, which is the square root of 1. So the area of this first rectangle is simply 1 times 1. The second rectangle, its base is also 1, delta x, times f of 2, so we're going to find f of x2. f of 2 is the square root of 2, approximately 1.41. 1 times 1.41 is 1.41. Third rectangle, same way. Delta x, which is 1, times f of x, f of 3, which is the square root of 3. When you multiply those together, you get 1.73. You do the same thing at 4. You get delta x times f of 4, which is the square root of 4, which is 2. The area of the fourth rectangle is 2. So to find the approximate area under this curve, we add up all 4 of the rectangles, 1, 2, 3, and 4. When we do that, we get approximately 6.14 square units. Now, is that perfect? Is that the purple area perfectly? No. It underestimates it with these triangular-looking regions. So it is a slight underestimate of the area under f of x from 1 to 5. Could we do better? Absolutely. If we looked at dividing this interval up into 16 parts, you can see that our estimate's going to be a lot better. That little error where we're underestimating the area gets smaller and smaller. Well, what do you think would happen if we made these rectangles infinitely small in width? We had thousands and thousands, really infinite amounts of them. Well, then we get the exact value of the area, and that's what calculus is going to do for us later. So what you'll learn today is to be able to understand the value of calculus, its ability to analyze a dynamic universe. Then we looked at the two major problems that led to the development of calculus, the tangent line problem and the area problem.